Now we have another question, 9.8. A piece of copper having rectangular cross section of 15.2 millimeter by 19.1 millimeter is pulled in tension with 44,500 Newton force, producing only elastic deformation. Calculate the resulting strain. Now, as you know that Young's modulus is longitudinal stress upon longitudinal strain. Therefore, strain is made as subject of formula that becomes stress upon Young modulus. Okay, stress is force upon area. So, force upon area divided by Young modulus. Okay, so that can be written as F upon A into Y, and force upon area is nothing but length into breadth into Young modulus. So this value you will get. Okay, place all the values which are given, length, breadth, everything is given. Okay, Young modulus is also given, force is given, and simplify, you will get this answer 1.27 10 to the power minus 3 as longitudinal strain. Now, a steel cable with a radius of 1.5 centimeters supports a chairlift at a ski area. If the maximum stress is not to exceed 108 Newton per meter square, or rather it is not the 108 Newton per meter square, try to understand, it is 10 to the power 8 Newton per meter square, that is 10 to the power 8 Newton per meter square. What is the maximum load the cable can support? Maximum stress is equal to maximum force upon cross sectional area, force upon area. Okay, stress is force upon area, so maximum stress is maximum force upon cross sectional area. Therefore, F maximum is maximum stress into area. Just we have to take a cross multiplication. Okay, maximum stress multiplied by cross sectional area. That is written here. Maximum stress should not exceed, it is given 10 to the power 8 into pi r square. Now here radius is 1.5 centimeter, so convert it into meter, 1.5 10 to the power minus 2 meter, and square of it. Okay, so if you multiply and simplify, you will get 7.07 into 10 raised to 4 Newton. That must be the maximum load that the cable can support. Now the next numerical number 10. A rigid bar of mass 15 kg is supported symmetrically by 3 wires, each of 2 meter long. Those at each end are of copper and middle one is of iron. Okay. Determine the ratios of their diameters. If each of the wire have the same tension, Young modulus of copper and the other one, that is Fe, that is iron, is given. Diameter of copper we take as dCu and diameter of iron we take as dFe. In area of cross section of copper we take as ACu. In area of cross section of iron we take as AFe. Now area is nothing but pi r square and r is diameter by 2, so it becomes area of copper to be pi into diameter of copper square upon 4. Similarly, area of iron wire is pi into dFe square divided by 4, so area of copper upon area of iron will be dCu upon dFe, the whole square you will get. Okay. Now as you know that Young's modulus is force upon area, that is stress upon strain. Strain is change in length upon original length. Okay, so this is general formula. Now strain in the copper wire can be F upon area of copper into Young modulus of copper, and similarly the strain in iron wire can be force upon area of iron wire multiplied by the Young modulus of iron wire. Now since each wire is to have same tension, therefore each wire has same strain. So the strains are compared, that of the two, that is of iron as well as of copper. So they are equated. Now just force will be cancelled out. Okay, Young modulus of iron upon Young modulus of copper can be written as area of copper divided by area of iron. And as you know, area of copper upon area of iron is dCu upon dFe the whole square, because this we have already discussed here. Okay, that we have already found. Okay, so instead of ACu upon AFE is nothing but dCu upon dFe the whole square. So it is substituted here and just write the values. Okay, we just have to write the values dCu upon dFe. Then this dCu upon dFe can be made as a subject of formula by taking the square root. So dCu upon dFe can be under root of Young modulus of Fe upon Young modulus of copper, and just place the values, take the square root because these two will be cancelled out. Okay, and you will get the answer to be dCu upon dFe as 1.256:1. Now we have the 11th numerical. The 14.5 kg mass is fastened to the end of the steel wire of unstretched length to be 1 meter. So it is having the original length as 1 meter. Okay. Now it is whirled in a vertical circle. So this way the mass was attached and then it is whirled in the vertical circle. Initially the length is 1 meter unstretched length. Okay, with a velocity of 2 revolutions per second at the bottom of the circle. Okay, in a vertical circle with an angular velocity of 2 revolutions per second, the cross sectional area of the wire is 0.065 centimeter square. Calculate the elongation of the wire when the mass is at the lowest point. Young modulus is given. Now see, here we have the value of omega. Omega is 2 pi f. Okay, so 2 pi f is the omega. So frequency is given. It is 2 revolutions per second, or number of revolution per second is frequency, and that frequency is given 2 revolution per second. So it is 2 pi f, so it becomes 4 pi radian per second. Now centripetal force is mv square upon r, and as you know it is v is equal to r omega, so it becomes m r omega square. This we have already discussed in earlier chapter. Okay, now when the load is at the bottom, or we can say lowest position of the vertical circle, then total force, try to understand, total force will be weight plus centripetal force. So mg plus mr omega square. Whenever the load is here at this point while whirling, then there are two forces, one is weight and the other one is centripetal force. So two forces are there, they are added, mg plus mr omega square, and their values are written of different quantities. Okay, m is taken common, g plus r omega square, place the values and just simplify. You will get the force to be 2429.5 Newton. Okay, now Young's modulus is stress upon strain, that is force upon area on change in length upon original length. So delta L, that is elongation, can be made as a subject of formula. Okay, because this formula becomes FL upon delta L into A. So delta L is FL upon AY because Young modulus will be FL upon delta L upon A. Sorry, delta L into A. So delta L can be FL upon AY. Place all the values. Force we have just now got. Okay. Length originally is 1 meter. Okay. Then simplify, you will get the elongation to be 1.87 millimeter. Okay. This is the figure which is explained earlier by me. Okay.